felt like we had, I was wearing y'all out. And so I finished up that chapter 11 with a 15-minute video that you need to watch if you haven't been able to watch it so far. I'm going to turn my video off to make sure that I have enough bandwidth. I brought my own hotspot because I don't trust hotels. So let's see if I can get things going here. Tonight, we plan to do, believe it or not, we plan to do module 12, 13, and 14. So 12 is IPv6, which we had planned to do last week, but I felt like I didn't want to wear y'all out last week. So we're going to start with IPv6 tonight and just a little bit of introduction to it. IPv6 is just big, more address space. IPv4 is 32 bits. IPv6 is 128 bits. So it really helps to show students just the sheer size, the number of bits we're talking about. Some way, a bunch. And there's examples up here. This is an IPv6 address. It looks daunting if you've never seen it.
I'm sorry, I don't
I'm not
believe
seeing your screen.
PowerPoint.
You're not seeing my screen.
Yeah.
That's because I haven't shared it. Y'all expect me to share it too? Wow. Thank you for telling me that.
Yeah, no worries.
See, I think I want to do screen one. I have a little portable extra monitor that I take with me. Is that better?
Know that we're awake. We are all awake.
At least you know we're engaged.
I appreciate that. But you didn't let me just keep talking. Okay. All right. So just the picture of the sheer size of the IPv6 address. Thank you for letting me know that. So when you first look at an IPv6 address, it's a little scary. But if you take it as a 16 bits, so there are 8 of these 16 bits here. And then if you take just those bits and think about them, translate them into binary bits, and then translate those, it makes it a little simpler to translate those IPv6 addresses. So this is 16 bits. And if you take one of those bits, is a nibble. I believe, didn't we used to call that a nibble when it was 4 like that? Y'all remember that?
Yep, that was it.
Okay, so it was a nibble. So if we write this 2001 as a hex number or in bits, let's see, I'm not going to be able to type on that in this. So let's see, maybe I can here. If we write, it's going to be too big. If we write that in bits, it would be 0010. It's going to be too big. And then 0000, 0000, 0001. I hope that's 16. See if I can place it there. No, that didn't work too good. But if we take the 2, 0010 is 2, and of course 4 zeros is 0, 4 zeros is 0, and then the 1, 0001. So that's too big, but hopefully you get the idea. So let me clear that off because that's not very clean. So this particular one, all zeros, would be 16 zeros out there. This one would be 0000, 0001, 0000, 0000. So it helps a lot just to be able to see the translation into bits, into binary bits. And I know this is kind of small. Hopefully you can see. Can you see this okay? Maybe if I share it's pretty small, isn't it?
Yeah.
Let me try to share my screen too and see if that's any better. Is that any better?
Yes.
Okay, that's better then. Okay, we'll go with screen 2. So I always like to show students, here we've got up here the hex place value up at the top. Go over there to that screen. There's the hex place value, 1, 16, 256, 496, 16 to the 0, 16 to the 1, 16 to the second, and then 16 to the third. And if I do that in 4 segments there, the number 15 then would be all the way over here, we'd have 1111. The number in decimal, the number 15 would be 15, and then the hex would be 000F. So if we have all ones, that's going to be 8 plus 4 plus 2 plus 1, which is 15. So we turn all those on, giving us that 000F. So decimal 15, hex 000F. Decimal 16 now is sort of like when we're adding 1 to the number 10 in decimal, you have to put a 0 and carry the 1. So we can't go up any higher because we filled out all the ones. So we add 1 to it and we carry the 1 over to the next place value. So 16 is 10000. And then 25 would be 00F9. And then 257 would be that 256 place value here, 256 place value. This is 25 here because we're using the 16 place value plus the 8 place value, 24 plus the 1 place value, which gives us 00F9. 257 then would be 0101. So
Hey,
we're
quick
using,
question for you. So when you're teaching the students, when they go for the exam, are they allowed to have scrap paper to do this, or is this just a whole memorization type of?
no, they you know, if you're talking about the certification,
Yes.
yeah, they get either one of the little write tablets or they get a piece of paper that they can write on.
Right. But
Yeah,
they would still have to remember to break these
yes.
octets down, or
And
yeah.
the first thing I tell the students to do is write your place values down. Again, I've divided this into nibbles here, but then I went ahead and carried the binary place value over as well. So really, they only have to think about typically only a nibble at a time, if that makes
Okay.
sense.
Okay.
But yeah, I have them write that down right away. Same way with binary, 2 to 0, 2 to the 1, 2 to the second, etc., all the way over to the 7th, and then the place values.
Okay.
So you can abbreviate IPv6 addresses. So we have this long IPv6 address here. Oh, my buttons aren't working right. And you can, if you have a leading 0 in any octet, you can omit the leading 0. If you have all zeros, you simply use a 0. A pair of colons can be used once within an address to represent a bunch of zeros. So here's the example from the curriculum. Here we have our original IPv6 address. We can shore this one down to 10. We can shore this one down to 10, this one to 10, leave the leading 0 off of this because significant digits would be to the right. And then what we can do here is we can bring this further down and have a double colon there. And students should know that if I have placeholders in every one of those hextets, 1, 2, 3, 4, 5, 6, that double colon would represent the 7th and 8th hextet of that particular IPv6 address. I don't know why this bar slipped down here. There's some other abbreviations. For instance, if you have FF01 colon, then all zeros colon 1, what you can do is boil it all the way down and have FF01::1, the double colon represents the missing hextets that are just zeros. You can only use one set of double colons in an IP address, and they have to be contiguous. So these right here are contiguous zeros. Here's another example, 3FFE, etc. So I can leave off my leading zero here, my leading zeros here. There's 1 0 here, the leading zero here, etc. So let's break it down and kind of make sense of it. So really, we're talking about a subnet prefix that's half. Typically, we're going to chop this in half. It's half of the IP address. What I mean by the subnet prefix is the network bits. So the network bits are going to be half of that IP address, and the interface ID would be the other half. We're used to seeing it just from last week, not really used to it if you're new to it, 255.225.250 or /24. You don't use decimal numbers at all in an IPv6 address. We simply use a prefix length. So that tells me, since there are 128 bits total in an IPv6 address, this one is split right down the middle. 3FFE, 1944, 100A, those are the network bits, and everything else is the interface ID. So what I have students do is I try to get a little ridiculous so they understand how you identify the network bits and host bits. So if I see that /64, I know that half of it is going to be network bits. 1, 2, 3, 4 hextets. So the answer is the network bits are half and the host bits are half. The network portion is the first 4 hextets. The host portion, if we bring out all those, that double colon that identifies contiguous hextets of 0, that's the host portion. On this one, you really want students to think about this. 96, that means there are 96 network bits. So that means there are 6 hextets that belong to the network. 1, 2, 3, 4, 5, 6. And there are 2 hextets that belong to the host portion. Just so students will understand what that prefix length means. Couple others. Here's one very similar. You have a /80. That means network bits 80. This prefix length, that's what it means. That's the network bits. And they should be able to understand 1, 2, 3, 4, 5 hextets that belong to the network and 3 that belong to the host. Here's another one. On this one, you just have 1 hextet that belongs to the network. Everything else is going to be a host portion. Got a bunch of hosts on that one. A little bit ridiculous, but sometimes you have to get a little bit ridiculous. So really, if we think about it, the prefix length is usually always 64, and then we'll talk about a circumstance that really needs it to be 64. You can go shorter or longer, and we'll talk about that in just a few minutes, but it's always recommended to deploy that /64 IPv6 address because it allows stateless address auto configuration, which we're going to do a demo in just a few minutes to look at stateless auto address configuration. With a IPv6 address, there are 3 kinds of address types. There's a unicast, so that's 1-to-1. In other words, if I'm going to send a packet to another computer, as long as I have that MAC address in my ARP table, the first packet may be a ARP request needing his MAC address, then that's a single unicast. Multicast is 1-to-many. That's an address for a set of interfaces maybe that belong to different nodes. Multicast addresses are 224 and above. Anycast is 1 to nearest, and there is no such thing as a broadcast address, not really with IPv6. Broadcast is an Ethernet / IPv4.
Question.
Yes, sir.
We still refer to the endpoints as hosts. Is that
Yes,
a
sir.
term? I noticed you didn't say host when you were referring to the unicast 1-to-1, you know. If I'm sending it from one computer, I send it to the other. Those are called hosts on
Yes,
the
sir.
network.
Yes, sir. It would be one host to the other address. To the
Okay,
other host.
okay.
Yes, sir.
All right. Very good.
So, and don't want to confuse you with this, but I just kind of want to show you the big picture. So here's our big granddaddy up here, IPv6. There's unicast, we just talked about, one host to another host. There is also a multicast, and we'll look at an example of that. Multicast is going to always begin with FF. And then anycast could be to a group. We don't really talk about that a lot. So what we're going to do IPv6, we're going to do unicast, and the two we're going to look at is global unicast and link local. Again, no broadcast addresses. So there are other, but for our purposes and for your purposes, really, we really need to know that global unicast and link local. Notice link local is FE, the multicast is FF. So here we are. We're going to, let me see if I can go back up.
I guess, Gabe, so the link local is always going to start FE.
Always, yeah, FE.
And multicast is always going to start FF.
Exactly. And I'll show you an example of that.
Okay.
So now, look, we've talked about global unicast. So we're over here. We're on the unicast side. And now we're down to global unicast, and we're going to subdivide it. There is a manual unicast, or a manual IPv6 assignment, we might say, that's static. And then we'll talk about EUI 64 in a moment. And then there's also dynamic, which is done stateless. We'll do an example of that. DHCP-v6, we'll just refer to that briefly because that's really in the next course. So let's look at the structure of a global unicast. Again, we're going to talk specifically now about global unicast. So we're over on the left side, unicast, now global unicast. So if we look at, and we're going to break this up, so if we look at the global routing prefix as N bits and the subnet ID as M bits, the rest of it is the interface ID. If we look at that, the range for a global routing prefix is 2000::/3 to 3FFF::3. So that's a lot of numbers. But basically, that just means it's routable. So a global unicast address is routable and unique. So I gave you you don't really have to know this bottom part here, but just know that if it's a 4 followed by some letters or numbers, it is not routable. It's not global unicast. Or if it's 1999, it's not a global unicast address. 314 rule, because I always have to have a rule, you know. So if we look at how to divide this thing, we have the global routing prefix that is 3 hextets. We have a subnet ID that is 1 hextet, and everything else is the interface ID. There's that /64. Even though we're calling this a subnet ID, typically this is used for subnetting, it's still 64 bits all the way over, including the subnet ID. The global routing prefix is assigned to us. So we might be assigned 2001 ODBA/48. We get that from our provider, let's say. So it is understood that the next hextet is for subnet purposes. And that's a lot of bits for subnetting. And in a minute, we'll talk about how you can change that if you need to. But right now, the 314 rule, first three hextets are the global routing prefix. The fourth hextet is a subnet ID, and then everything else is the interface ID. So here's an example. The global routing prefix, notice I didn't give you a prefix link, we're assuming 64. The global routing prefix is the first three hextets. The subnet ID is 3333, and the interface ID is the rest. So let's say we were assigned 2340.1111 :::::48. Our global routing prefix is here. Now we take that fourth hextet and we say, okay, there's my subnet. And that shouldn't say 1 in hex, it should say 1 in binary, sorry. So that's my first subnet right there. You can use the 0 subnet in IPv6. Yay! And you can even assign it as 0 all the way over. There's my second subnet. There's my third subnet. There's my 10th subnet. But we wouldn't write it like that. We would write it with :1, : : fill with zeros till we get to that 128. Very simple subnetting. We're just going to increment this by however many we need to for the subnetting. Some special IPv6 addresses. This is a default static route, which we'll talk about later. Mostly I want to point out again about that link local unicast. You've all seen the Microsoft 169 address when you can't get an IP address from the DHCP server. Basically, it's the same thing. 169 address would work on a LAN. So it's similar to that Windows auto configuration. FF something is multicast. Okay, the link local, extremely important. It is dynamically created on an IPv6 interface by using a specific link local prefix and a 64-bit interface identifier. We're going to see an example of that and how it's generated dynamically. Now we can make it up, and if you've done any labs in this, and I think a couple of you have, you've noticed that they're having you make up and they're assigning that link local address. You recognize it because it usually starts with FE8 for that link local. Those are the ways you can see the IPv6 addresses. A real important command is IPv6 unicast routing. Nothing will work IPv6 wise without this command. I don't know, some of you may be old enough and remember this, but when I first started teaching routing, you had to use the command IP routing on a router in order to have routing work. Well, now it's part of the feature set and you don't have to have it on there. But you have to have IPv6 unicast routing in your configuration if you expect to use IPv6 addressing. It's got to be done. You can disable it with a no form of command. Just real quick, just to show you a management issue, you wouldn't have to use all 64 bits for your subnet. You wouldn't have to use them. Maybe you don't want to use all 16 of these for subnetting for management purposes. Maybe you just want to, we get this from our ISP. You can't change the first 3 hextets, but we can do anything we want to with this 4th hextet. How we manage it, it just depends. We can break it into nibbles and say, okay, there's 48, 49, 50, 51, 52. I want to make this /52 and grab these for the network and then let everything else be subnets. Or we may want to go all the way over to 60 and make it a little more management with not so many subnets. So that's just a FYI, that's bonus material there. But typically we're going to use 64. Okay, now I want to do a little demo. Got to figure out which screen I can put that on. I've got it open. So that's, move that over there. and I've got my monitor set up opposite. Okay, so we're going to set up a little bit about IPv6. And what I did, I went ahead and configured the router with the IPv4 address with 10.0.0.1. And then I've got this PC configured with 10.0.0.2. And I'm just going to ping my gateway v4 just to make sure that I can get it. There's that over there too. So I'm going to ping 10.0.0.1, and I've got my gateway, so that's good. Just so you know that this link is up and working. So now what I want to do is I want to come over to the router, and I don't remember what, y'all excuse me, I'm having to manipulate these things. I don't remember what that is. That's gig 00. Okay. Okay. I didn't name it or anything. I'm just doing down and dirty here. So let's look at show IPv6 gig 0, v6 gig 0, 0, 0. Show interface IPv6 gig 0, 0, 0. Oh, goodness. Okay. It's not, let's see what I do wrong here. Show IPv6. Interface.
Didn't you say before you have to config to do it to IPv6?
Not for a show command.
Okay.
I wanted to show that I have no IPv6 running there. I should have been able to enter my interface number, but I couldn't for some reason. So show IPv, there is no IPv6 running. Now I'm just going to turn it on with IPv6 unicast routing. Oh, now I do need config T, CONF. IPv6 unicast routing. Okay. Now I'm going to go and repeat that command. Y'all have no idea what I'm dealing with here in this motel. Okay. Show IPv6 interface. Oh, okay. Still no IPv6. But I had to use that command IPv6 unicast routing in order for what I'm fixing to do to work. So now I'm going to go into that interface, gig 0, 0, 0. Ah, it's gig 0, 0. No wonder. Narrow-minded. So now I'm going to, I think it's enable. No. I'm just going to enable IPv6. I'm not going to do anything but just enable it. I just turned it on. Now I'm going to go show IPv6 interface. It should work now. Look how much I've got just by enabling. I haven't done anything else, but I turned on IPv6. Now, what it's done, it's already generated a random link local address. IPv6 is enabled. Link local address is FE80. I've already got a link local address. It's ready to go. And look at this. It's already got multicast addresses. I believe this is all nodes. I believe this is all routers and so forth. And it's got all of the configurations that IPv6 uses just by turning it on. I didn't put an IPv6 address on it. I just enabled it. So now I'm going to go over and I'm going to go ahead and put an IPv6 address on it with the right interface this time, just for grins. And let's use IPv6 2001 address 2001. Let's do DB8. Notice I left the leading 0 out. ACAD or Academy. It's handy because I can remember that. Doesn't matter if it's capital or whatever it is. A. So right now I've got 2001 DB8 ACAD A. So which one of those is the subnet octet?
Is it the DB8?
The A is, because it's the 4th hextet. So the first 3 hextets are global unicast, are the network prefix, and then the 4th subnet is still part of the 4th hextet is still part of the network, but it's the subnet ID. And then I'm just going to say 1/64. Okay, so let's look at that. Show IPv6 interface gig 00. Now look at that. I've already got another multicast joined. And now I've got a global unicast address. Notice it gave me the address that I typed, and it also gave me the subnet. So the subnet, that subnet prefix, the first 4 hextets is 2001 DB8 ACADA. I actually could have just done :/64 and put it as a 0 address, but I always like to start with a 1 to avoid confusion. So now I've got that turned on. I've got IPv6 address running. So I'm going to go over here to this PC. I don't know why it wants to open on the other screen. We'll move it over. And what I'm going to do, notice, and I meant to look, notice the link local address is already generated. I'll talk about that in just a few minutes. But now I'm going to click automatic, and let's watch what happens. Wow, that was fast. Does this address look familiar? That's the address that I configured on the router gig interface going toward the PC. This is called stateless auto address configuration. 2001 DB8. Let me bring up the router over there. Put this on the top and put the router on the top as well. Get over there. Let me bring up the router. Get them on my little screen here. So if we go up, there we go. So there's my local address that was automatically generated, 4601. And if we look here on the default gateway, it's the same address. So using that link local address, the router sends out a router advertisement. The PC is doing router discovery, and it discovers there is a router within that LAN, if you will, and it says, oh, it's FE8290CFF, and I need to get an address from that global unicast address, which it was there somewhere. There it is. There it is. 2001 DB8 ACADA. So I'm going to grab 2001 DB8 AC80A and look at this. 260, 2FFF, FE4A, AC45. Does that look familiar? That actually is mostly the MAC address from that PC. So now we find out that the MAC address, which is already a hex number, is being used in the IPv6 addressing. And so it's a random generated number, but it's not really random. It's just using the MAC address. Why not? It's already there. So we can change things up a little bit. We can make this router over here IPv6 address FE80 ::3 local. And when I toggle on the PC from static to automatic, it picks up that FE80 ::3. Again, because the router is using router advertisement, the PC is using router discovery to discover the address. That's so cool to me. Whoever thought of this was pretty brainy. So now I have a default gateway that works just fine, and I'm just using my FE80. So this FE80 is not going to be used outside this LAN. It's not going to be used outside what's going on between the PC and the router. It cannot be routed because it's not a global unicast. As this 10 cannot be routed because it is private IP addressing. A little bit different, but still it's not routed. So that FE80 or FE8 link local is used to talk between the router and the host. Router discovery, router advertisement goes back and forth. If I put another PC on there, I wouldn't have to do much. So let's just throw one on there. Speed it up here. I don't even have to put a V6 address, a V4 address on it because I'm just doing V6 here. The right one, yeah. So I'm just going to go to the desktop and I'm just going to say, bam, I want an IPv6 address. And it should get it. IPv6 address failed. I do wrong. I shouldn't need a IPv4 address. Let's see. Really shouldn't even need that. Don't you love it when your demo doesn't work? Let's see about the switch, what's going on with that. FA02, and that's 3. For some reason, it's not seeing it. Let me start over. I apologize. Hopefully you see the principle, though. Okay, I must not have connected it. I must have connected it to something else on that PC. That's all I can think of. So now let me try it again. And let's toggle. Oh, it's already gotten the address. So there we go. 6E4C. Again, that's the MAC address off this PC. A lot of times what I do, have the students do is have them look at the MAC address on their computer. And there's some things you can play with this. What happens is basically the MAC address has to be padded to work for IPv6. So what it's going to do is put that FFFE string in the middle between the OUI and the local address. So 02E08, or it might be 2E08F, and the 2D6E4C, that's the OUI of the NIC address. So see how it splits the two, and then the NIC specific and the OUI, and it pads it with that FFFE. Pretty brilliant, if you ask me. Questions about that so far? Does it make sense?
You lost me.
I lost you?
Yeah, you lost me. I was waiting for to see the address on your diagram before I'm convinced that this works.
Okay. Well, I mean,
I
what do
see IPv4 addressing, but the new PC that you added, I was hoping I would
but
see.
I just typed that in there so you'd
Oh,
know
okay.
what address was there.
Oh, okay.
Yeah,
You
I just
typed those.
let's
Okay.
see. Let me go here and show you on the router. Let's just do a show run so you can see everything. So there's interface gig 0C8, that's 10.0.0.1. There's the IPv6 link local. There's the IPv6 address.
Okay.
By the way, I just did this to show you step by step. You don't need that if you have the address on it. You don't have to enable IPv6. I was just being facetious to show you what happens when you turn it on, even without an address. But that's just on the diagram because I just typed it on there.
Okay. All right.
Does it make sense now? Now that you're seeing the running config, you know that it really is there. In fact, we can go over here and do the same thing. Okay, let's go to command prompt here. IP config, pconfig. Remember, if it shows it here, it should show it all. Yeah, there's on the PC, there's the link local address, its own link local address. Let's see what we've got here. That's Bluetooth. There it is. There's the IPv6 address. This continues on the next line. There's IPv4 address. There's the default gateway that we changed to FE80::3. It has both the default gateway for V6 and V4. It has a lot of other features. IPv6 has a lot of duplicate address detection, a lot of other ones that we don't really go over in this first course. Does that make better sense to now that we've seen it in the configuration of both devices? I'm getting crickets. Did I completely lose y'all?
No, I'm still with you, but I thought you were putting together a combined network. What was the term for it, where you could have IP4 and 6 on the same network?
I don't know if there's a term for it. It's just you're running both protocols on the same network. Yeah.
Yeah. Well, that's what I thought I was looking at.
Okay, I see.
Okay.
Yeah, I am. I'm running both. In fact, with IPv6, you can have multiple IPv6 addresses on any one interface. Kind of blows my mind, but you can. IPv4 doesn't work that way, but with IPv6, you can have multiple IPv6 addresses. other comments, other questions? Let's see if everybody's still awake.
That sparks the question, why would I want to have multiple
True,
addresses?
true. Well, I wouldn't. I wouldn't. And really, this also begs the question. When you think about IPv6 and Slack, what I just showed you was just a pure demo, so you could see the power there. There's a problem, right? Look at this little placeholder here, DNS. Whoa, I have no DNS server. Now that's a problem. So there are actually 3 different ways to run IPv6. This is Slack, this is easy. The second way is to at least have the gateway address and the DNS server in it. And the third, and that's called a OBIT, other bit. And then the managed bit is where you have a DHCP v6 server, which is the way I would have it. So I can give it the range that I want it to have, the range of IPv6 addresses, my DNS server I want, my gateway, and all that stuff that I need to give it. This was just a kind of a funky thing to show how v6 behaves for the advertisements. That was my whole purpose, to see the advertisements. Okay, we're going to go on to chapter module 13 if we're good to go. Yes, no, maybe, good to go?
Yeah, I think we're good to go.
Yes.
Okay. Okay. All right, let's see. Let me move him over there again now. There he is. All right. Module 13. We already talked about this, but I did want to do an activity. That reminds me. Let me get that activity from the curriculum. To log back in. I made sure it worked just before we came online here. And I want to go to 11.2.4. We'll just do a couple of these.
Yeah, if you're showing the activity, we're not seeing it. I'm still
Getting
looking at
there.
the
Yeah,
PowerPoint.
thank you. Thank you for
Okay.
reminding me. Okay, now see if I can move him over there.
There we go.
This is just a, let's see, that's gonna have to make it smaller if I can. There we go. Can you see that okay? Kind of, sort of.
Yep.
Okay, so let's start this. So we've got an IP address of v4, and this is back to just unicast, broadcast, multicast. So the question is, click the host or hosts that will receive a packet based on the address type, unicast, broadcast, or multicast. So which one of these hosts down here will receive this this packet? That's the kind of stuff you need to kind of think through, because that really kind of gives it out. So if it's going to 100.5, that's a unicast. So this guy should get it. Let's check it. That's correct. So that's 1-to-1. We're sending that packet. So let's get another one. So there's 237, 192, 126, 17. Who is going to get that one?
.4.
Pardon me?
I guess this 192.168.100.4. Bottom right.
Yeah, 192.16.17 group. Is there anybody else that has that 237? This is a,
Oh, I can't even see.
yeah, it's hard to see. It's very small. And I believe this one too, right? 237. Okay. So let's check that. Okay, that is a multicast destination address because it's above that 224. So it's in that above the range of 224. So it's multicast, more than one. Let's get another problem. There's a unicast address. That's an easy one. Which one will get that one?
The one on the, I guess, bottom left.
Lower left.
Bottom left, right, because that's a unicast. Okay, that's correct. One or two more. That's another easy one. That's a 100.2.
Same place.
Same what? Same
Yeah.
one. We didn't get a new problem, did we? And that's the same one that we've already gotten. If you see if you see something above 224, you know that it's multicast. So those kind of activities in the curriculum are helpful to go through those. Anycast is one the closest. That's you want to access a website that has servers in different countries. Anycast would help you connect to the closest server best for you. It's not fixed like a unicast address. It's fixed. You're going to this particular address. Anycast, you're going to a server that satisfies your requirements. Okay, so let's talk about IP fundamentals and protocols. There's our friend, the OSI model. We're going to talk a little bit about now IP, a couple of things we use with IP, transport layer, and UDP. That's those chapters. So IP is the network layer, transport layer is the TCP and UDP. So those are basics. We need to know that like we can breathe. IP is network, transport is TCP, UDP. Okay, choosing a protocol. Let's see if I can get this. Y'all use Ink to Go. It's handy if you can. Yes, it's handy if you can get it. So choosing a protocol. So there's TCP, there's UDP, there's ICMP. That's kind of what we're going to talk about. Well, first of all, we don't really choose a protocol. So an application developer does, like an online game developer, is going to choose the protocol that he's using in his game. So we mostly use TCP IP because it is reliable between two endpoints. So if I can draw a line here. So let's say there's an example. Here we are sitting at home and we want to make a deposit to our bank, or let's say we want to move $100. My dollar sign's going to look really bad. We want to move $100 from my checking account to my savings account. So we're going to use TCP IP because it's reliable between two endpoints. So what we're going to do, we're going to click the button and say, I want to transfer that to the server. Well, we want some kind of acknowledgement. So this server, we're wanting some kind of acknowledgement that he's got it. We should have a button that says done, finished. And we call that an acknowledgement. So TCP is going to acknowledge that you've gotten that deposit. It's reliable. TCP is reliable between two endpoints. So have that acknowledgement. And if your PC has sending a packet and he does not get an acknowledgement, he keeps sending, he's sending, he's sending, he's sending. He's not going to be happy until he gets an acknowledgement back the other way that says, okay, I got it. And he will keep resending it till he gets an acknowledgement up to a certain point. So that's how important that TCP protocol is. You typically see TCP IP because it's part of the same stack. UDP is a little different. So UDP is unreliable. So I use an example. My son goes to Argentina a lot. And so he calls me on WhatsApp. I don't know if y'all are familiar with the WhatsApp app. Have y'all used that? It's a free app and you can make calls on it. And it's cool. It's just IP.
Yeah.
But
Mhm.
but it uses UDP because it's real time. So we're having a conversation and he's telling me about, so he's up there and I'm down here. He's telling me about his day. He says, we went, and all I hear is we went in a cab. And I'm going, okay, well, where did you go in a cab? Well, the word downtown was lost because it's real time. It's real time. It's just dropped. It's real time. There's no acknowledgement because UDP is used typically for voice. So there's no acknowledgement, but it's because it has to be real time. If it was TCP, he'd have to say we, and then give it a moment to make sure I heard it, then went, give it a moment, make sure I heard it. So we're sending and acknowledging, sending and acknowledging. That's so it's UDP. So it's not sent later. So with TCP, it'll keep sending like we're sending when we want an answer. Did I really make this deposit? But with UDP, it's real time. So there's no overhead. It's faster. So that's kind of an example of UDP, if that makes sense. Okay, so ping uses ICMP. So we talked about TCP and UDP. Let's talk about ping. It shows layer 3 testing. So the other day I pinged cisco.com and noticed that the DNS server, wherever that was, is going to map that to the IP address. And I get 4 replies. It sends a small packet of data and waits for a response. So there really isn't a ping. It's really called Packet Internet Groper, and it uses ICMP. So this particular one shows that we've sent 4 requests or 4 packets and received acknowledgement, and there is 0 loss. So over here, we see that there is 0 loss. Very important, 0 lost packets. And it shows a minimum, maximum, and average round trip. So it was sent 4, we received 4, we didn't lose any, and it shows us the minimum time and the maximum time. Probably the first one took a little bit longer, so it averages those out. See. So ping actually uses 2 protocols. Ping itself is not a protocol. ICMP is the protocol. So it actually uses 2 protocols. So if I ping from here to here, I'm sending an echo request. So I'm sending an echo request. That's a request. If I'm sending something back, that's a reply. And really awful writing with this pencil. So echo requests, they even have 2 different TCP ports. I think one is 8 and one is 7. So ping is not the protocol. Ping uses the protocol called ICMP. Echo request, echo reply, and it's for diagnostic purposes. Engineers use this all the time. And a lot of places don't allow pings. Patrick, do y'all allow pings on your campus?
We do
Okay.
on certain networks, yeah.
Okay, gotcha. Our organization doesn't. Of course, we're a tier 2 ISP, and so we have to be really careful. But it's diagnostic. And then there's another one that is also used, and that is called traceroute. And I did a trace on, this is our domain, esc11.net, where I work. Notice that it is a very old IPv4 address. We've had it many, many years. When IPv4, we bought a block, the 216 blocks, and that's our main server, 216, the public address anyway. So a command, and you can't see it up there, the command is TRACERT on the PC, and the command on the router is actually trace space route. You can use just trace, but trace space route. So that traces the route from the source to the destination. It uses ICMP. Each line shows a router with a round trip time. So one of these lines right here shows the round trip time it took to get there. And notice all my pings and all my trace routes are going to start at ATT Wi-Fi Manager. That's my gateway at home. It would be different here. So it just 1 millisecond because it was right there in the room. And notice we hop really quick to a 12. We get some timeouts, all right, but Zayo used to be, Patrick, you might remember, I think it used to be part of AT&T, but that's basically our provider now, Zayo. And so finally I get this, and you might have some timeouts, but at the very bottom of this, you'll see trace complete. So it completed the trace. The default hops is 30. So a maximum of 30 hops. So if you don't get a ping, you don't find the trace route after 30, it'll just stop. But actually I did get a ping. So you can use trace route. It also helps to trace the route and see how many routers you're actually going through. So TCP model, IP finds the destination of the mail, and TCP has the work to send and receive the mail. So TCP is the workhorse. Remember, IP hands it up to TCP in the OSI model and says, here it is. Hope you get it. I ain't checking, but TCP is going to check. So what TCP does is divide the data into packets at the sender's end, and the same packets have to be recombined at the receiver end. So it's really kind of an interesting process. So I wanted to show this video, if I could bring it up. It's a short video.
My name is Lynn Root. I am a software engineer here at Spotify, and I'll be the first to admit that I often take for granted the reliability of the internet. The sheer amount of information zooming around the internet is astonishing. But how is it possible for every piece of data to be delivered to you reliably? Say you want to play a song from Spotify. It seems like your computer connects directly to Spotify's servers, and Spotify sends you a song on a direct, dedicated line. But actually, that's not how the internet works. If the internet were made of direct, dedicated connections, it would be impossible to keep things working as millions of users join, especially since there is no guarantee that every wire and computer is working all the time. Instead, data travels on the internet in a much less direct fashion.
Many, many years ago, in the early 1970s, my partner Bob Kahn and I began working on the design of what we now call the internet. Bob and I had the responsibility and the opportunity to design the internet's protocols and its architecture. So we persisted in participating in the internet's growth and evolution for all of this time up to and including the present. The way information gets transferred from one computer to another is pretty interesting. It need not follow a fixed path. In fact, your path may change in the midst of a computer-to-computer conversation. Information on the internet goes from one computer to another in what we call a packet of information. And a packet travels from one place to another on the internet a lot like how you might get from one place to another in a car. Depending on traffic congestion or road conditions, you might choose or be forced to take a different route to get to the same place each time you travel. And just as you can transport all sorts of stuff inside a car, many kinds of digital information can be sent with IP packets, but there are some limits. What if, for example, you need to move a space shuttle from where it was built to where it will be launched? The shuttle won't fit in one truck, so it needs to be broken down into pieces, transported using a fleet of trucks. They could all take different routes and might get to the destination at different times, but once all the pieces are there, you can reassemble the pieces into the complete shuttle and it'll be ready for launch. On the internet, the details work similarly. If you have a very large image that you want to send to a friend or upload to a website, that image might be made up of tens of millions of bits or ones and zeros, too many to send along in one packet. Since it's data on a computer, the computer sending the image can quickly break it into hundreds or even thousands of smaller parts called packets. Unlike cars or trucks, these packets don't have drivers and they don't choose their route. Each packet has the internet address of where it came from and where it's going. Special computers on the internet called routers act like traffic managers to keep the packets moving through the networks smoothly. If one route is congested, individual packets may travel different routes through the internet, and they may arrive at the destination at slightly different times or even out of order.
So let's talk about how this works. As part of the Internet Protocol, every router keeps track of multiple paths for sending packets, and it chooses the cheapest available path for each piece of data based on destination IP address for the packet. Cheapest in this case doesn't mean cost, but time and non-technical factors such as politics and relationships between companies. Often the best route for data to travel isn't necessarily the most direct. Having options for paths makes the network fault tolerant, which means the network can keep sending packets even if something goes horribly, horribly wrong. This is the basis for a key principle of the internet, reliability. Now, what if you want to request some data and not everything is delivered? Say you want to listen to a song. How can you be 100% sure all the data will be delivered so the song plays perfectly? Introducing your new best friend TCP, Transmission Control Protocol. TCP manages the sending and receiving of all your data as packets. Think of it like a guaranteed mail service. When you request a song on your device, Spotify sends a song broken up into many packets. When your packets arrive, TCP does a full inventory and sends back acknowledgments of each packet received. If all packets are there, TCP signs for your delivery and you're done. If TCP finds some packets are missing, it won't sign. Otherwise, your song wouldn't sound as good, or portions of the song could be missing. For each missing or incomplete packet, Spotify will resend them. Once TCP verifies the delivery of many packets for that one song request, your song will start to play. What's great about the TCP and router systems is they're scalable. They can work with 8 devices or 8 billion devices. In fact, because of these principles of fault tolerance and redundancy, the more routers we add, the more reliable the internet becomes. What's also great is we can grow and scale the internet without interrupting service for anybody using it.
The internet is made of hundreds of thousands of networks and billions of computers and devices connected physically. These different systems that make up the internet connect to each other, communicate with each other, and work together because of agreed-upon standards for how data is sent around on the internet. Computing devices, or routers along the internet, help all the packets make their way to the destination, where they're reassembled if necessary in order. This happens billions of times a day, whether you and others are sending an email, visiting a web page, doing a video chat, using a mobile app, or when sensors or devices on the internet talk to each other.
Okay, so I thought that was
Save on over 400 wines during Spec's huge wine sale. Cheers to savings.
Hi, I'm Carrie-Anne and welcome to Crash Course Computer Science. The internet is amazing. In just a few keystrokes, we can stream
Okay, so I went all the way back, didn't I?
Yep, he did.
Okay. So I wanted to show a couple other things in the curriculum. Let me go back to the curriculum here. 14.5.1. So go back in here, 14. And this just, again, I'm gonna make that bigger. The pond video explained TCP really better than I could. But just a little bit about this, if you haven't read this before, because it can be confusing. When we talk about clients sending TCP requests, the example here, client 1 is requesting web services. So that's port 80. That's TCP port 80. And client 2 is requesting email services, which is port 25. So 2 different TCP ports, port 80, port 25. So client 1 needs web services. Client 2 needs email services of the same server, and this guy's taking care of it. Well, when this client 1 is sending a request for HTTP or HTTPS or World Wide Web, whatever, the destination port is going to be 80 because that is the port that the server uses for HTTP. However, this other port, this 49152, is kind of a randomly generated port that keeps track of the conversation between this client and the server. Even though the server is hardwired, when it comes back, it's going to have 80 on it, but it knows to send it to 49152 instead of 51152. So you've got to have a source port. We already have a source IP and a destination IP. Now we've got a source TCP and a destination TCP. So the destination, if we're requiring HTTP server, is going to be port 80. But the source port is going to be a randomly generated number from that asker, the one that's asking for those services. So there's the destination ports. Destination 80 here, destination 25, that's the well-known port numbers. The request source ports are again dynamic port numbers generated so that the conversations can be kept track of. So we know that we've got a request from 49152 for HTTP services. And we've got a request from 51152 needing SMTP or email services. And then when it goes back the other way, the server knows that I need to distribute my port 80 HTTP response to 49152 because that's where I got it from. And I need to give my SMTP, my email, to 51152 because that's where I got it from. So hopefully that helps. HTTP request, source port 49152, destination 80. Then when we get to the connection, we've already talked about this a little bit. The initiating client requests a client-to-server communication server. So they're going to send a request from A to B, sequence of 100. When B gets it, it's going to say, I'm acknowledging that you sent 100 because I'm incrementing it by 1. So here's acknowledgement 101 and sequence 300. So now I'm sending an acknowledgement of my session that I've got it, yes, because I've incremented it by 101, pardon me. And after you get that acknowledgement and that synchronization, now you've got an established sequence. I got the sequence 101. I'm acknowledging your acknowledgement, and I'm incrementing it by 1. And so you have this window that goes back and forth, and that's how it kind of keeps track of conversations. And when the client has no more data to send, it's going to send a segment with the finish flag set. Sending the finish received. I'm acknowledging that I've got it. I've acknowledged your receipt of that. Step 3, now I'm telling you I'm really finished, and then I've acknowledged it back. So we call that a sliding window, basically. Acknowledgement of 3. It's really 4. It's really 4 steps. The three-way handshake is called the three-way handshake because you're establishing that the destination is on the network and it has some kind of service like HTTP or email services, and informs that destination that we want to communicate with you, back when we saw that other example. If you'll notice here, this is the TCP header, and we talked about the IP header. But the thing I want to point out here is the acknowledgement. We've got a sequence number, an acknowledged number. This particular one is a window of 16. Let's go on down here to reliability. The video talked about the reordering of segments. So TCP doesn't really send packets. IP sends packets. TCP breaks those packets into segments. So when you want to associate a word with a TCP layer in the OSI model, you want to think about segments. And as I showed in the Khan Academy, different segments may take different routes. So what TCP does, it divides that data into segments because maybe it's very complex data. And what it does, look at it, it's receiving it all out of order, but then TCP is going to reorder it so it's in the original order. They're kind of placed here in a buffer until it can reorder it. And then if it arrives out of order, they're going to resequence it. TCP can resequence it. And then there's also a retransmission. Duplicate segments. I don't know if you've been able to read this or not. This TCP provides method of management segment losses. When we've got a sequence number and an acknowledgement that's incremented by 1, it tells us, well, I haven't received it. You better send it again. 3 and 4 were sent and not acknowledged, so they have to be resent. Let's see, what else do we need to talk about? This just shows the flow control TCP layer of the OSI model. Also is really big on flow control. And I know some of you attending this class are not going to go for the completing the course, maybe taking the final exam and taking all the testing that requires you passing it. Some of you, I think, I know are taking it for the information. Some of you, I believe, are going to go ahead and take the course, do the labs, do the final exams. Is that right? Do I have that right before I go on here?
Yes, I think some of us are going to go down the Cyber Ops route, and
Okay.
some of us are going to continue down the CCNA path.
Okay. So the reason that you really needed to take this is because you need to understand, particularly TCP is very important in cyber ops because you're really examining things at the packet layer and the segment layer in TCP. Okay, let's go back to here. I can find it. Right. Okay, I wanted to do some subnetting review questions. And I've got, let's see if I can, I already gave you the answer. Let's see if I can do reading view. Make that smaller. And bring up my spreadsheet so we can work on answering these together. Okay, and my spreadsheet is here. really prefer doing this at home. It's so much easier for me to have everything right there. Okay. Still not sure you can see all of that. Let's see. I take the ribbon off and I forgot how. Awkward. Okay. Let's try it. Okay, so just a review in subnetting so that we kind of refresh ourselves. So we have these 172.16.195.233 and 172.16.222.240/19. 19 means that the subnet mask is using the first 19 bits right to left. So the subnet mask is going to be 11111111 1111. That's 16, 17, 18, 19, 2, 3, 4, 5, 6, 7, and all zeros. So we talked about anding. I think I've got one too many there. 1, 2, 3, 4, 5, 6, 7, 8. I do. Okay, 172 would be 128, and 32 is 160, and then I need 12. Okay, so 172 is 128. I don't need 64. 32 would be 160. And then I need 160. I don't need, it's wrong. 101, 0, 128, 64, 32, 16. So I need a 8 and a 12. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 172, and I believe that's 195, 191, and 233. So if we remember the anding, if it's two ones, it's going to return a 1, a 0, 1, 0, 1, 1, 0, 0. And if we remember when we anded, we should get the same exact number. If it's all ones, we get the same number that we started off with, 1, 1, 0, 0, 0, 0, 1, 1, and 190. If I and these two together, I'm going to get 0, 1, 1, 0, 0, 0, 0, 0, and 233 is going to be, should be all zeros. All right. So the decimal number after anding is 172, 195, 191, 0. That's right.
0.
Okay. No, that would not be right. This would be 64 and 32 is, no, that should be right.
Yeah,
yeah,
that's right.
Thank you. So I'm telling you, I'm working in a hardship tonight. So, or in which subnet? So the answer would be
191. Very first one.
160. 160.
160?
We did it wrong. Let's go back to this now. So the subnet mask is in binary. The subnet mask was 19. So that would be that's right. 16. And then after anding, it would be 0, 1, 1, 0, 0, 0, 0. So that should be
Yeah, it should be A. Unless we did something wrong.
64, I think we did something wrong.
Excuse me for talk. Let me mute
No,
myself.
please, I obviously need help tonight. So 191 after ANDing, so this is 191 in binary. Because it's 255 minus 128. No, that's not, yeah, that's 191. Because this one would be no, that's not 191. So I need 128. And I need 0 and then 1, 2, 3, 4, 7, 8. That's what we did wrong. So now that should be 1, 0, 1, 0, 0. Right now? So that should be after ANDing, that's 128 and 32 is 160.
Yep.
Does that make sense?
Yeah, you got me on that one. Okay.
Okay, so in binary, 191 is this number. The subnet mask is 16 bits over. So that's 19, 16, 17, 18, 19. When I AND the 191, my problem was I didn't have 191 down there right. I get a 1, 0, 1, and then 5 zeros. So that's 128 place value. We don't use the 64, but we're using the 32, so that gives you 160.
Okay.
Just a little review for us. Okay, let's do another one. Maybe we can get this one right. I wrote it out a little bit just to help us remember. You must request a network from 172.30.00/16 that supports 50 networks. Now, when we're looking at this, we already have 16 bits that belong to the network, right? So 16 bits belong to the network. Move this down. So let's do 172.30 and 0, 0, 0, 0. So we're not going to be ANDing this time, really. So if we have this octet and this octet for networks, what we want to do is 50 networks. How many octets, and this is all really needs to be zeroed out here, so let me. So how many bits would we need to borrow from the third octet for 50 networks? Remember, that would be actually 8 zeros. Oh, I don't have that. Let me customize that. I think I have a custom set out. So how many bits would I have to borrow for 50 networks? 2 to the what would be at least 50.
2 to 5, 2 to the 6.
Yeah, I'd have to borrow 6 bits.
Yes.
Yeah.
2 to the 6.
2 to the 6. So let me goes away. So I would have to borrow 6 bits. So if I borrow 6 bits, that means I'm turning on 1, 2, 3, 4, 5, 6. No, not 6 bits. Yeah, 6 bits. I'm turning on 1, 2, 3, 4, 5, 6, 7, 8. 6 bits. So what would my subnet mask be?
Oh boy.
So here's 16 bits. 17, 18, 19, 20, 21, 22. And there's 22 / 22. And, or another way of putting it would be you add up the place value of 128, 64, 32, 16, 8, 4, it would be 252. So either one, C or D, would be correct.
Okay. That's good. I'm rusty. I was. That's
Well,
good.
it's hard to do it on the fly. Okay, so yeah, that's right. Okay, I think I have a couple more. Okay, let's look at this. We've got, what are the next two valid subnets after 192.168.32.144/28? Well, with this, if we're starting with that IP, what I'd do, I wouldn't even look at the answers. I'd want to look at all the subnets. So I'd probably go over here and I'd say, let's see, 192.168.32 and 144. Okay. Customize that already. So I need to know first of all, I need to know what the subnet mask is. The subnet mask is 28, which means I'm borrowing, I borrowed 4 bits from my original.
Right.
Right. So I borrowed 2, 3, 4, 5, 6, 7, 8. That's not going to show it. So I borrowed 4 bits. So my increment is, I borrowed 4 bits. My increment is 2 to the 4th, which is 16. So if my increment is 16, the next one after 144 is 144 plus 16, which is 160.
Mhm.
Then 176.
Cool.
So really all I have, go ahead, I'm sorry.
I said, cool. just
All I have to do is look at the increment. It's /28. That means I borrowed 4 bits from the 4th octet. And all I have to do is 2 to the 4th, 16. That's my increment for my subnets. If I back it up, what's the one before this? Testing your arithmetic skills here.
Yeah,
All
I was
I
going
do
to
is
say it'd be
subtract
minus 16 there, but
too late in the day for that. So it'd be 128. See how those numbers crop
128.
up all the time? How about the one before that? 28 minus 16.
Yeah, be 112.
112, right. Okay. So those numbers crop up. Okay. Which of the following is a valid subnet mask? So tell me which, this is an easy one, which 2 would work as a valid subnet mask?
AB?
C,
A and C.
C and D. Yeah.
Yeah, you can't,
Oh, I didn't see you.
you can't go from
Oh.
small to larger.
Oh,
on
I
the
said
subnet mask.
252.
Yeah.
I
I know. It's too late to tell a 2 from a 5, right? Okay. Let me stop this, and I want to discuss one more thing with y'all. Let's see, I'm on full screen 2 again. Okay. So let's look at the schedule. Next week, I hope I can be at home and do this. So we're right here on the 17th, and we did 12, 13, and 14. Next week, we're going to do 15, 16, and 17. I need to know how many of you are going to want to take the final exam and the final skills exam. Now, I'm not going to just say, here it is. We're going to discuss a way that we can do it successfully, because we've gone through this way too fast for y'all to be completely perfect in it. So I need to know how many of you are going to be taking that final exam and try to pass this course so that you're accredited in it. You want to just email me separate? You want to just email me separate?
Yeah.
Okay.
And when we take the finals, May 1st?
Well, you can take it when you're ready for it. I don't care. We can take it
Okay.
anytime. I don't know what your plan is for beginning cyber ops. We'd want to finish with this. And what we might want to do is that final exam, I usually just make it 10% of the grade, and the labs are like 30%. The module exams are 20, and I make the skills a whole lot more. What we might want to do is have a real good review for the skills
Okay.
together as a session for those of you going on to do that, and make sure you understand what skills you need to. If you've done the labs, and about 3 of you, I think, are doing those labs and working through them, and you should be making good notes because all skills are always open note. Even with students, always, if they have journal, they should be making journals and making notes on every task. So all they have to do is refer to their notes. The problem I always see with students is that they, imagine this, that they make their journal notes the night before, and so they can't find anything. But if they will make those notes, as we go along and make those copious notes, it really helps. So, yeah.
Hope everybody knows she's talking about us.
No, I'm not talking about you at all, sir. Not at all. But if some of you want to go ahead and complete this and get accredited in it, I would encourage you to do that, and I'll help you with that. We'll work through it together and make sure you have the skills. You know what they are. You know what's going to be on it. I'll show you the labs that you're going to do. The final exam, you have to take that to be passed, but we can take that together too. And you know what? We won't make 100 even with my help. I've never made 100 on a Cisco exam. I always tell my students, if you made 100, you cheated. So,
I guess is the exam, is it a pass-fail type of thing, or is it?
The skills.
Yeah.
I actually wrote an activity creator. So like your labs that you do, they give you a grade. Except I don't have the check results button active.
Gotcha.
So you more or less have certain items you have to do, and we can work through one together. I'll give you a sample one, and do it together, and then I'll give you another one very similar to it. Because I feel like we've gone through this like fire hose type thing. So, but I know that some of you do want to get accredited in this, and I would encourage you to do that. I know 3 or 4 of you do. So I'll work with you on that. I mean, it doesn't have to be by May 1. We can.
Yeah, because I was about to say, and I think Chris was alluding to it earlier, that around that May timeframe, we're gearing up for commencement and graduation, and that's the thing. We're entering towards the semester, and we're dealing with some of that. So, I think if we could, if it doesn't have to be by May 1, we can kind of maybe delay that finals a little bit, maybe later in May. I think that would be helpful for myself.
That's fine. I don't have a deadline. You all chose the time you wanted in. I'm very flexible. I don't care.
Okay.
I just would like for you to have success if you want to finish the course. That's
Right.
what my hope is. So you're accredited in it, so you at least have that. And instructors do need an 80 on the final, both on the skills and the multiple choice. The multiple choice, I don't worry that much about because these questions are very difficult. Y'all have taken questions and they're very difficult. So I really put more stock in the skills that you have. And most of you have done the lab, so you're already developing those skills. The stuff that we went through the night, TCP, UDPs, windowing, all that stuff is hard to get. So, and that's the kind of things we'll see on the written final exam. So we want to make sure that we maybe even take that together.
Okay.
So, and there's a practice exam as well. So, other questions or concerns?
How many questions is the final?
I think there's 50.
Okay.
Yeah. And what we can do is we can set up a
So
time.
you can only miss 10.
See,
I get
Chris has
redos.
got his math. His math is perfect.
Yeah. Okay. All right. That's all I have to say about that. If there's anything else.
No,
No.
I think I'm good.
All
Good
right. So,
session.
all
Good
right.
session considering you're not at home and
yeah,
coming off
is
of
for
a golf
this
course.
is for the birds. Doing this at a motel and having all this is next week. I'm at home doing it, hopefully.
Sure.
So y'all have a good week, and let me know if you need anything.
All
Very
right.
good.
Sounds good. Thank
Thank
you.
you.
Yeah.
Okay.
Thank you.